here is more example. Assume that there are 4 different web pages. So each node represents the web pages, and we have the hyperlinks, right? So page D, and the web page, maybe this is the Wikipedia web page, and for example, the Sungkyunkwan University has a link to the artificial intelligence department, the Wikipedia. So because it is part of the Sungkyunkwan University, right? And something like that. That is the definition of the hyperlink, right? So we have 4 web pages, and assume that I said that, so we think the page rank is a probability distribution, right? So which means we can get a value from 0 to 1, right? For each node, right? We may say the score is the PR. Each page rank score can have the value between 0 to 1, right? Oh, I wrote down here. And the score, the page rank score of A is defined as the sum of the page rank score B and C. Oh, where's D? B, C, D, right? Because they send the boat to A, right? So the A score is defined by the other web pages, right? Very simple, right? And another assumption is we also need to count the outbound link. So make it a little bit more complicated and more precise. So to get the score, the page rank score of A, we're considering the outgoing link as well, because the B send the link to page A and C, which means the page rank score is divided by 2 different web pages, right? So we just give the page rank score B over 2, right? It has link from C, right? But C has just one outgoing link, right? So we just add this. We also have link. The page A has the link from D. How many outgoing links from D, right? We count 1, 2, 3. So that's why we put this. So PR of D over 3 is added. So this is how to compute. Very simple, right? So we can formulate this computation using matrix. We have many benefits when we formulate the computation using the matrix. So we introduce new terminology, M. So M is column stochastic adjacency matrix. So each element in the matrix represents a probability. So that's what we call stochastic. And we also call this as a column stochastic adjacency matrix because the sum of the elements in one specific column, the sum of the value Oh. Which means all different row, right? This is 1, right? Sum of the all element at the jth column, sum of the all elements equal to 1. So this means this, and all the value is the between 0 to 1, right? So it has 3 outgoing links. So that's why we have the 1/3, 1/3, 1/3. The sum is still the same as 1, right? In here, the same as right. So when have the h between j and I, we have this value. All right. And then, so now we also introduce new notation. So to represent the PageRank score using the vector, so one-dimensional vector. So this is the same as the PageRank of the node I. But this is the important score of node I. The sum is equal to 1. So previously we summed up using the outgoing link, right? Now we can get the matrix formulation, right? So let me give you the example. We have four by four matrix, right? One A, B, C, D, A, B, C, D. This is M, right? So let's start with the simplest one. So what is the simplest one? The C has the outgoing link toward the A, right? Maybe 1, 0, 0, 0, right? So what about the D? So D has outgoing links toward B and C, right? The B has A and Z. What about A? We don't have the outgoing link. So let's assume it has some link toward the D. So we get, oh, not here. So D, right? Oh. Zero, 1, right? This is the same, and so for the initial score, we just give, we also need to have the 4 different values for the each node, right? A, B, C, D. We just put 1/4 1 over 4, 1 over 4, 1 over 4, right? When we just multiply this, we get something, right? So we just compute the A's score. So we call that is the Y, the R hat. R hat A could be computed. How to compute that? We consider this and this, right? 0 plus, oh, plus 1, right? Is that same as you expected? So previously we computed the PageRank score for the node A. So it has no connection from itself, and from B has 2 rings, right? And we use the PageRank score of the page B, and we consider for the C has 1 ring, so 1 is here, so we're considering the initial score. D D has A and C, right? So yeah. That's why we need the students during the lecture, right? So, what's like here, right? And we have 2 outgoing links from D, and the score is computed like this. It's exactly the same as the previous computation, right? So this one. So we just modified a little bit more. So anyway, conceptually, still following the previous computation. So we're still computing the same information, even though we use a matrix formulation, right? So in the previous computation, we started with the initial PageRank value, and then we propagated the PageRank score by considering the outgoing links, right? And then we have updated the PageRank score, right? This one matrix computation, and now we have the R hat, right? We can consider the time information. So at the time t, let's assume that the PageRank computation is just served for the random jump. So in that sense, the PageRank is quite similar to the random walk, right? So could you remember the previous lecture? The drunken guy jumped into the connected node and considering the connected neighbors and randomly choose the uniformly random choose the one of the neighbors and go to the one of the link, right? The one of the nodes, right? So in that sense, quite similar to the random walk, right? The PageRank is similar, so the behavior wise the same as the random walk, because at the time t, server at the specific page I, for example, the server. So in this case there is no drunken guy, so we have a server, the server is on the sum page I at the time t. The next time, considering the next node and moves one of the neighbors at random, it is connected to all the desks. We just move to here. And this is exactly the same as the PageRank, because the PageRank score of this node, let's say this is the jth node, the RJ score is, in probability, it is decided from the nearby neighbors, and it is affected by the node I and this and this and this, and their probability, the server's probability, and likely to be visit this node at the time t plus 1, we get this, right? So from this intuition, this is the overall probability, so not considering just this. So it is this analogy, and I would like to say the page rank is there. The jumping is the same as the jumping the behavior of the random one, right? So now we know this, the matrix computation for the page rank computation, and when we keep multiplying the matrix M, the multiplication of the matrix M is the same as the multiple propagation of the PageRank score, right? We started with the initial score of the PageRank of each node. Considering the outbound link, we keep propagating. We keep computing this one, this one, and this one, this one, and we expect some stationary state. Stationary state means it's likely to converge some score, right? We keep propagating the score and score and score, the scores, and we expect all the nodes paging scores are converged towards some values, right? Converged to some values. That is called stationary distribution. So we would like to compute this. So notation wise, we keep multiplying. We have some score, even though we multiply the matrix M, we're still getting the same score. So that indicates the R follows a stationary distribution of the random walk. When you see this multiplication, we just put the constant on 1. They're still the same, right? But it looks like a eigenvector eigenvalue computation, right? This is from the definition of the eigenvector and eigenvalue. So we'll expect to the input matrix A. We try to get the eigenvalue. So the multiplication of the U is the eigenvector of the A, because it is the constant times of the same eigenvalue vector matrix, and we get the output from this computation. So this is the definition of the eigenvector and eigenvalue, right? So considering this is our input. The R is eigenvector, and 1 is eigenvalue, right? So computing the page rank is the same as computing, getting the eigenvector, right? We have the A, we have the M. From the graph, we can construct, we can synthesize, we can just compute, just mathematically, not just numerically compute the M, right? Considering the outbound links, we can get the M. We just compute the principal eigenvector. That is the same as the page rank score. So that is the how to estimate, how to get the eigenvalue, the page rank score.